Okay, this is a lesson about graphing rational functions. A rational function is basically a fraction of polynomials. We're going to be identifying the asymptotes, vertical, horizontal, slant asymptotes, as well as holes. You should pause the video now and try to do this problem by yourself. If you don't know how to do it by yourself, please put your pencil down and just watch the video, learn from me, and then pick your pencil back up and go ahead and do the problem by yourself. But please don't copy along with me as I do the problem, because you won't really learn how to do it that way. The best way to learn is by doing it on your own after you learn how, of course. Alright, so let's take a closer look at number one. I always start by looking for the horizontal asymptote. It's pretty easy to identify. The horizontal asymptote is the one that depends on the degree. If the degree of the numerator is less than the denominator, the asymptote is y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals a over c, where a and c are the leading coefficients. If the degree of the numerator is greater, then there is no horizontal asymptote, but it might be a slant asymptote. So let's take a look at which situation we're in. Alright, the numerator has degree 2, the denominator is degree 1. So since the top degree is higher, there is no horizontal asymptote. So we might as well go ahead and write that down. Horizontal asymptote, none. Okay, now let's talk about the slant asymptotes. If the top degree is 1 more than the bottom degree, then there might be a slant asymptote. Okay, I say might because we have to make sure that the denominator doesn't cancel out. So we could try to factor this, or a fun thing to do would be to go ahead and try to find the slant asymptote. The way you find the slant asymptote is by dividing. So long division is the way to go on this one. So let's do it. We're dividing 2x squared plus 5x plus 3 by 2x plus 3. Now, in order for there to be a slant asymptote, there has to be a remainder. If there's no remainder, that means that the denominator actually gets canceled out. So let's take a look. We look at the first term in both polynomials, and we ask ourselves, 2x times what will make 2x squared? Well, that's x. I'll put it in the x spot. Then you distribute. X times 2x, of course, is 2x squared. X times 3 is 3x. Alright, next we change the signs in order to subtract. So this becomes negative and this becomes negative. Alright, so these cancel out. Positive 5 and minus 3, that's 2x. Bring down the 3. And you basically start over again. Okay, so 2x times what is 2x? Obviously that's 1. Alright, put it in the proper column. And then you distribute. 1 times 2x is 2x. 1 times 3 is 3. Okay, when you go to change the signs in order to subtract, what you find out is everything cancels out. The remainder is 0. Okay, remainder 0. That means two things. That means there will not be a slant asymptote. But the reason there will not be a slant asymptote is because 2x plus 3 divides evenly. That's, no remainder means it divides evenly into the numerator. And basically, we can take this x plus 1 and use it to factor at this point. So this is what really just happened. So we had this 2x plus 3. Now that we see the 2x plus 3 divides in evenly, then we know that it must cancel out. That means one of the factors in the numerator must be 2x plus 3. Alright, so that's going to cancel out. Guess what the other factor is? Yeah, it's the quotient, x plus 1. Okay, 2x plus 3 times x plus 1 would give us back the original trinomial. And you can check it, 2x times x is 2x squared. 3 times 1 is 3. And you know how I like to say inner plus outer equals middle. Well, inner we have 3x, and outer we have 2x. Alright, add those together, and what do you get? 5x. Alright, so this is factored correctly. So like I said, normally we would have a slant asymptote, but the reason why we don't is because the 2x plus 3's actually cancel out. So instead of having a slant asymptote, what are we going to have? What do we get when things cancel out? When things cancel out, we get a whole. Okay? And the way we get the whole is by setting this factor equal to 0 and solving. So we've got, if we set the 2x plus 3 equal to 0, okay, this is going to tell us where the whole is. So by the way, this also means there will be no vertical asymptote, okay, because the denominator canceled out. So vertical asymptote, none. So there won't be any asymptotes, but there will be a whole. Alright, so I've got 2x equals negative 3. If I divide by 2 on both sides, I've got x equals negative 3 over 2. Alright, so that tells me that there is a whole at negative 3 over 2. Alright, of course I need the y value to go with it. How do I get that y value? Well, I evaluate what's left of our rational function. And all that's left is x plus 1. Now I couldn't use my calculator for this, but that would be a little silly because it's so simple. I might as well manually substitute negative 3 over 2 for x. Okay? If I do that, if I take this negative 3 over 2 and plug it in for x, okay, what I'm going to get is negative 3 over 2 plus 1. Okay? You shouldn't need a calculator for this, but just in case you do, have one handy. Alright, negative 3 over 2, whoops, negative 3 over 2 plus 1. Okay, that is negative 1/2. So that's the y value. Okay, so I have a whole at negative 3 over 2 comma negative 1/2. For graphing purposes, let's think of this as negative 1.5 and negative 0.5. Okay, so let's graph that whole right now. So negative 1.5 and negative 0.5. So we'll have a whole right there. Okay. Now, so there are no asymptotes because look what's left of our function. Alright, this is the part we're going to graph. Our function has now been reduced to f of x equals x plus 1. Okay, it's just this with a hole in it. So this is just a line. It's a linear function, plain and simple. Y equals mx plus b. This 1 is the y-intercept. Okay, so there's my y-intercept right there. And the slope is 1. You know what I mean? Up 1, right 1. Okay, so I can just make the slope from there. Alright, you get it. It goes forever. Alright, so let's just go ahead and graph that. So your graph is going to look like this. Okay, alright. Let's take a look at number 2. Alright, once again, the numerator degree is 1 higher than the denominator. So right away that means there will be no horizontal asymptote. So I can go ahead and put none. Maybe maybe there's a slant asymptote because the numerator degree is 1 higher. But only if the 2x plus 7 doesn't get canceled out. Now, looking at the fact that I've got a 3 here, there's no way that this 3 is going to factor and give us 7. So there should be a remainder. So let's go ahead and try to find the slant asymptote, which you get by doing the division. So let's go ahead and do long division and find the slant asymptote. Okay, so we will do 2x plus 7 divided into 2x squared plus 5x plus 3. And we ask ourselves, 2x times what is 2x squared? That's x. Take that and distribute. X times 2x is 2x squared. X times 7 is 7x. To subtract, we change the signs. Okay, these cancel out, and these make negative 2x. And I bring down the 3. And I start over. 2x times what makes negative 2x? That's going to be negative 1. I take that negative 1 and I distribute. Negative 1 times 2x is negative 2x. Negative 1 times 7 is negative 7. To subtract, I change the signs. So this becomes positive and this becomes positive. These cancel out. This becomes 10. Alright, so that's my remainder. So that's going to become x minus 1, and then I do plus 10 over 2x plus 7. Okay, so there is a remainder, so that means I will have a slant asymptote. So by the way, this is the quotient form of the function. Alright, it's just a different form of the same thing. If I graphed the original function, and then if I graphed this form of the function, it would look exactly the same. So, but only part of this is the slant asymptote, and it's the part that I've shown here in pink. So the slant asymptote is y equals x minus 1. Okay, y equals x minus 1. Now, it doesn't matter whether you get it from here or here, but this form of the function also helps us find the vertical asymptote. Alright, because we will have a vertical asymptote if we set this 2x plus 7 equal to 0. So let's do that. Okay, I'm finding the vertical asymptote now. So, subtracting 7 from both sides, 2x equals negative 7, divide by 2. So I have x is equal to negative 7 over 2. So this is going to give me my vertical asymptote. X equals negative 7 over 2. Okay? So nothing cancels out, alright? That's why I have a remainder. So since none of the factors cancel out, then I won't have any holes. Okay, so that completes this. So let's get the graph started. Let's go ahead and graph our vertical asymptote and our slant asymptote. First of all, the vertical asymptote, this is negative 3.5. So we'll think of it that way to help us graph it. Okay, this is negative 3.5. Okay, so we'll graph it right here. So there's my vertical asymptote. Now the slant asymptote is just a line. Alright, this is a linear function. Y equals mx plus b. So this -1 is our y-intercept. So we'll begin here. The slope is 1. So think up 1, right 1. So that's just going to be going up at a 45-degree angle. And you can trace it back the other way as well. Alright, so continue and we'll graph it from there. So there's our slant asymptote. Alright, now let's go to the graph to find some values to help us graph the function. Pay attention to the vertical asymptote because we're going to want values on the left and values on the right. So let's see. Now it really doesn't matter whether which one of the forms you use. You could put in the original function, or you could use the function in quotient form. Either way, you're going to get the same graph. Alright, so let's use our TI-30XS multi-view. Hit the table button, clear out whatever's in there, and go into fraction mode. And let's see, so we have 2x squared plus 5x plus 3. So 2x squared plus 5x plus 3. Whoa, I didn't do the squared. Okay. Alright, and then in the denominator we have 2x plus 7. So 2x plus 7. Okay, like I said, pay attention to the vertical asymptote. So our vertical asymptote is right here at -3.5. So let's use, let's look at -4, -5, and -6. So I'll start at -6. Okay, so -6 is our start value. Okay. You know what would be fun to do? Hit the table button again. Go back. Starting at -6. See here where it says step value 1? Let's let the step value be 0.5. Okay, by doing that, it'll give us the whole numbers and the decimals, so we can have more points to choose from. Okay, so at -6, we're at -9. Okay, so at -6, we have a value of -9. Okay. At -5, we're at -9.3. Okay, so that's just down just a little bit. Alright, how about at -4? At -4, we're at -15. Interesting. Okay, so at -4, we are at -15. That's right here. Okay. Let's see what's going on a little bit further to the left just to complete this curve, but you can bet that it's going to follow that asymptote. But let's take a look. Out of curiosity, I wonder if there are any whole numbers over here. Okay, well we had that. Any more whole numbers over here before I run off the graph? I guess not. We're out of whole numbers. Alright, so let's just use what we have. Okay, so for example, -7 is -9.4. Let's go a little further than that. Let's go to -10. At -10, we are at -11.8. Okay, -10, and this is being -11.8. Okay, so that's enough for us to see what's going on with this branch of the function. So let's go ahead and graph that branch. Alright, something like that. Now let's look at some values to the right of negative 3.5. Okay, so let's start at negative 3. Okay, so at negative 3 we're at negative 6. I'm sorry, at negative 3 we're at positive 6. Okay, so at negative 3 we're at positive 6. What about negative 2? At negative 2 we're at 1/3. Alright, so that's just a little bit above the line there. What about negative 1 and 0? Alright, at negative 1 we are at 0. Okay, what about 0? At 0 we're at 3/7. Okay, that's not very much. That's almost halfway. Okay, let's go a little bit further over, like around 10 or so, and see where we are. Oh, okay, there's a nice even number. So at 6.5 we're at 6. Okay, so at 6.5 we are at 6. Okay, so that's enough to give us a good sketch. Alright, so that branch will look something like that. Alright, and that's it. We sketched the graph. That's great. Alright, so that is it for number 2. Alright, last one. Once again, the numerator degree is higher than the denominator. That tells us that there will be no horizontal asymptote, so we can go ahead and put none. Maybe there's a slant asymptote because the top degree is exactly 1 more than the bottom, but only if there's a remainder when we divide. Alright, only if the x plus 1 doesn't wind up canceling out. And the easiest way to find out is just to go ahead and divide, because either way we'll need to divide. Since it's a simple x plus 1, synthetic division is the way to go. So x plus 1 means we'll put a negative 1 here. Our coefficients are 2, 5, and 3. Okay, bring this down. 2 times negative 1 is negative 2. Add, you get 3. 3 times negative 1 is negative 3. That is 0. That means no remainder. That means the x plus 1 is going to factor out. It's going to cancel out. So that means there will be no slant asymptote. So right now, as soon as I see the remainder is 0, I can go ahead and put none for the slant asymptote. Okay? Now, if I were to put this back into the form of a function, this 2 and 3 means that we're looking at 2x plus 3. Okay? So I'm writing it this way because this helps me to factor. So if I look at that original function, what's happening is the numerator just factored as your 2x plus 3, okay, that we just got right here, and times x plus 1. Okay, the x plus 1 divided in evenly, so that's how we knew, basically. You know how, like we used to do. We used to say that negative 1 gives us a factor of x plus 1, remember? Same thing, we just factored this thing. Okay, so we factored the numerator. The denominator is x plus 1. So because those remainder 0, we were able to do this. That means these x plus 1s cancel out. Alright, that means there will be no slant asymptote, and there will be no vertical asymptote because no more denominator. Okay, the function that's left over is f of x equals 2x plus 3. Okay, this is the function that the simplified version, but there will be no vertical asymptote. Instead, there will be a hole, because that's what you get when things cancel out like this. Okay, we are going to have a hole. Okay, if I take this x plus 1 and set it equal to 0, alright, subtracting 1 from both sides, okay, we are working on a hole. Okay, that tells us that there is a hole at negative 1. Negative 1 comma something. I just need the y value to go with it. Well, normally I take the remaining function and put it in my calculator, but this is so simple it would be a little silly to do that. It's quicker just to take the negative 1 and substitute it for x right now. So if I do that, this is going to become 2 times negative 1 plus 3. Okay, so that's negative 2 plus 3. So that's 1. Okay, so that's my y value. Okay, so negative 1 comma 1. We might as well graph that. Okay, so there's our hole at negative 1 comma 1. Alright, now let's graph the rest of the function, and we'll do that by graphing the simplified version of the function. Okay, so we're just going to graph this. Now this is just a line, a linear function, y equals mx plus b. That tells us to start at a y value of 3. So the y-intercept is here. And then use the slope. Okay, the slope is 2. So that means 2 over 1. So I'm going to go up 2 and right 1 repeatedly. So if I go up 2 and right 1, it's going to be doing this. Okay, it would hit right here if there weren't a hole there, and it will repeat in the other direction. Okay, so just go ahead and draw your graph through these points, and you'll be done. And that's it. That's what this function is going to look like. Just a line with a hole in it. No asymptotes, vertical, horizontal, or slant. Alright, that is it for this lesson. I hope it was helpful. I will see you on the next video.
No copying.
Wait, there's this last little part at the bottom I forgot about. Compare and contrast the graphs and functions. What makes one different from the other two? Well, the one that's different from the other two is clearly the middle one. Alright, the middle one has 2 branches. It has vertical asymptote and slant asymptote. Whereas other than the hole, the other 2 functions are just linear functions with a hole, no asymptotes. What do they have in common, the 2 functions that just turned out to be a line and a hole? Well, we said it as we went along. There's 2 ways you could say it. Problem number 1 and problem number 3, the numerator divided evenly into, the denominator divided evenly into the numerator. There was no remainder. Another way to think about it is the denominator canceled out a factor of the numerator. Okay, either way you want to look at it, that's what happened in number 1 and number 3. No remainder. Denominator canceled out. Okay, so if anytime that happens, you're just going to have a linear function with a hole in it. Alright, here I just wrote up what I just said. I'll just read it to you. Function number 1 and function number 3, I guess I should say in function number 1 and function number 3, the denominator divided evenly into the numerator, no remainder. This means that the denominator cancels out with one of the factors in the numerator. Thus, there will be no asymptotes, but rather a linear function with a hole in it. Okay, so that's what happened with number 1 and number 3. Okay, however, function number 2 is different because the denominator does not divide evenly into the numerator. There is a remainder. Thus, there will be a slant asymptote and a vertical asymptote. Okay, that's what happened with problem number 2. Okay, there it is. Now we really are done with this lesson. I hope it was helpful. See you on the next video.
And don't copy Daddy's video.
That's right. Maya is correct. I hope you're not copying along with me, because you really won't learn anything that way. Make sure you go back and have the ability to do each one of these problems by yourself.